Okay, good morning. Let's get started for today. This is class two. So we met on Wednesday and we discussed LPs, and I sort of gave you introduction broadly to LPs. So today I want to continue with that, um, discuss it slightly more broadly in the context of convex optimization, and then we will start on the geometry of linear programs. Okay. So, a few things just as a reminder. So, one is these classes will run Wednesdays and Fridays 10 to 12. I am trying to upload handwritten notes before the classes. I'll try to do it every week. The course is based broadly, in fact, very extensively on this book, Introduction to Linear Optimization. Okay. So, if you are really, I mean, for the PhD students here, you should be reading the book. Uh, but for even for the online audience, if you really want to understand the material better, you should be looking at the book. You should be maybe trying out some of the problems there. And I'll be happy to discuss things. I take ideas from there. Some of it I will bring in my own stuff. Some things I think are more important, maybe some are less important, but it's a very good book. So you should be looking at the book carefully. Okay. It's a great way to learn the subject. It's the way I learned the subject basically when I was a PhD student. I went through the book carefully. I think if you are interested, I mean, for the PhD students, yes, it's important, definitely. But for those of you online too, it's a great book to look at. Okay. So the class is on this book. Okay. Largely based on this book. Okay. The second thing is just as an announcement is there's a website for the course which is just linked to my website. So if you go to my website, the URL is up there. Uh, uh, but if you just Google my name, you'll find a link to my webpage, and you can search out for the graduate course on linear optimization. I will try to put up the lecture videos after the class, and I will try to put notes. I will also give you some problems to work on from the chapters just for you to practice. For the students here, I will be asking you to submit in some of those for your assignments, basically. Okay. Okay. Um, okay. And lastly, it's a PhD class, so it's important that we have enough time to discuss. Okay. So I will be covering material, but we should be having enough time to ask questions. I mean, so you should be feeling completely comfortable asking me questions. Okay. I mean, and it's obvious, but still, I just want to make sure. Please stop me whenever you either don't understand something, or maybe there's something you want me to correct. I did some typos, or you want to just have a discussion on some topic. You want to talk about something else. That's fine. If I feel it's not appropriate, I will steer the conversation. But please interrupt me. The best thing of face-to-face classes is you can ask me questions at any point in time. Okay. And for those people joining online, please, you can also unmute yourself and just ask me a question. Okay. And I will try to answer it. Okay. So feel free to unmute yourself if there's something you want to clarify. Okay. I will try to check on the chat, but if I can't check, you can just unmute and ask me. Okay. Okay. So let's get started then for today. Um, so just before I get started, for the online folks, can you hear me? Can you see the screen? Can you just give me a thumbs up if you can? Okay. Thank you. Okay. Let's get started then. Okay. Okay. So I want to just start by first just reminding what we covered last week. Sorry, last class. Okay. Of course, I won't be doing everything, but let's just get a quick reminder where we were. Okay. So the main thing I did last time was to try to introduce. So just a reminder from last class. I tried to define this class of linear programs. Okay. So I tried to define what this class is, and we saw there are many definitions that you can use, but two forms which you can use to represent linear programs. One of them is this form, which is to minimize C transpose X subject to AX greater than equal to B, where the input of this problem are these three objects: the objective coefficient function vector C, the matrix A, and the vector B. Okay, so this is a LP which has n variables, and there are m constraints. Okay, so the size of the linear program will be determined by n and m. Okay, and in general, when we talk about complexity, we will talk about using the bit complexity of the numbers in C, A, and B. Okay, but at this point, you can think about the size of the LP grows as n and m. So if n and m increase, the LP gets larger. So we are hoping ultimately to have algorithms that when n and m go larger, we should be able to solve it still efficiently as a function of n and m. Okay. There's a second form that you can also write all linear programs in, which is to minimize C transpose X subject to AX equal to B, X non-negative. Okay. In this problem, again, the input is clearly C, A, and B. There are n variables again. Okay. In this formulation, there are m equality constraints. Okay. So the input of this is there are m equality constraints, and these n variables here are all non-negative. So in principle, if you think about this linear program on the right, there are n plus m constraints because all these variables have to be non-negative, so they're also constraints. So in principle, there are n plus m constraints, but we will typically, when I talk about the simplex method for standard forms, we'll be looking at n and m where m is the equality. So the way you count things, you just be careful, but there's an n and m which will make sense for you depending on the context. Okay, these two forms we can go between these forms, and there are other forms also one can use. Okay, so we did this last time, and then we saw I think 4 examples last class. Okay, so the examples we saw was we saw one example in so we saw the diet problem, we saw the optimal transport problem, or the transport. It's also called the transportation problem. Okay, we saw a scheduling problem, and we saw a revenue management problem. Okay, these were 4 examples. Uh, I just picked 4. Okay, you can pick many other types of problems if you wanted to. Okay, and as we go through the course, we will do it. But some of this you will do in your exercise questions. You will practice formulations for other applications. Okay, but one of the things with linear programs clearly is it's a very practical tool because it solves practical problems. So there are practical problems out there that you can model using linear programs and integer programs. So it's naturally, so it's not just of mathematical interest, it's of practical interest too. Okay, so there is this, um, which makes it extremely useful and important. Okay, so I think with this, I will continue with today's material. Is there any questions from last time that is on your mind before I get started? Okay, doing these transformations, moving between transformations and stuff should become natural tools for you. Okay, as you do these formulations, it might be in linear programming or in other optimization problems. Some of these transformation tricks will still show up. Okay, they'll be useful for you. Okay. Okay. So today, what we'll do is we will. So today, my goal is to start to spend a large part to just talk about convexity. Okay, and there is a reason for this in the sense that convexity is a very important property which helps for which optimization problems often become much easier to solve. Okay, and I'll make this. We'll be careful about the definitions. And linear programs is an example of a convex program. Okay, so I want to first discuss this more broadly. Then we will talk about linear programming as a special case and some generalizations. Typically, if you're taking classes in optimization, you might take a class in convex optimization too. Okay, so there will be follow-up classes generally in optimization. You will take a full class potentially in convex optimization. There are very good books on this topic. Uh, I can just refer you to a couple of books at this point. So there's a book by Stephen Boyd and Levin Vanderberg. This is one book. So it's called Introduction to Convex Optimization. It's a good book. It's a good book that talks about convex optimization broadly and many applications of it. It's very accessible for engineering students. Okay, there are of course other books which are more mathematical in flavor. So there's a book by Terry Rockefeller. It's called Convex Analysis. Okay, which is a much more of a math book. Okay, and that talks more about just convex analysis. Okay, so it's less about applications and algorithms. It's more about the theory. Okay, Okay. So of course, we're not going to be doing these books here. It's not the focus of a class, but it is important that we think about linear programs more broadly in a class. So I do want to make this connection today. Okay. Okay. So these are two good books on this topic. Okay. They're the authors. You can just go to their websites and you'll find books on them. Their books. Okay. Okay. So let's first start with what's a convex set and a convex function. Okay. So a set X in Rn is convex if for all x and y in this set and for all lambda, which is a real number that takes values between 0 and 1, lambda x plus 1 minus lambda y also lies in the set capital X. Okay. So I'm looking at sets in Rn. So what's a convex set? So take any 2 points in the set, x and y. Take any scalar value between 0 and 1 and take what is called the convex combination. Take lambda times x plus 1 minus lambda times y. This should also lie in the set X. Okay, that's the definition. Okay, so let's look at some examples. Okay, should be a bit. My drawings are not always the best, but we'll get there. Okay, so take the set. Take any so what is a set? The set is all the points which are on the boundary and in the interior of this region. Okay, that's my set X. Okay, take any 2 points X and Y. What is the point lambda x plus 1 minus lambda y telling me? It parameterizes all points between x and y. Okay. So every point, so lambda x plus 1 minus lambda y are all the points along this line segment as lambda varies between 0 and 1. So for example, when lambda is 1, I will get x. When lambda is 0, I'll get y. When I take lambda equal to 1 by 2, 0.5, I'll get a point between x and y. What does the definition tell me? You take any 2 points x and y, every point that lies in the line segment between them is going to also lie in the set X. Okay, so that's a convex set. So this set is convex. Okay, this is actually what is. We will see later that this is a type of regions, feasible regions that we will see for linear programs. Okay, they are called polyhedron. We'll come back to this later. Okay, here's another example of a convex set. An ellipse. Okay, take a point. Let's take the point X, and let's for now take a point Y. Let's say even on the boundary. Okay, every point between X and Y lies in this set. So this is also a convex set. Okay, so both of these are examples of convex sets. Okay, and of course this definition, remember, is for every X and Y. Okay, so for every pair of points. Okay. Okay, so here's an example of a non-convex set. So again, think of all the points which are on the boundary and within the interior of this region. So these are all my points. Okay. So you can find for this set 2 points such that the points in the middle may not lie in the set. So for example, if I take this point to be X and if I take this point to be Y, there are points along this line segment which do not lie within the set. So that's a non-convex set. Okay. Here's another non-convex set. This is also non-convex. You can check this. You can find points X and Y such that points in the middle may not lie in the set. Okay. Okay. So is the definition clear for a convex set? Okay. Okay. So what's a convex function? So a function f, and we're going to define now the domain to be Rn to R. Later on, we'll restrict this domain, but for now, think of a function which goes from Rn to R. A function f going from Rn to R is convex if f of lambda x plus 1 minus lambda y is lesser than or equal to lambda times f of x plus 1 minus lambda f of y for every lambda between 0 and 1 and for every x and y in Rn. Okay, so that's my definition of a convex function. So, so what is this saying? You take, so again, let's do an example. By the way, the previous two examples of convex sets I showed you were in 2 dimensions. We'll look at, I mean, there are, of course, this can be in n dimensions. Okay, and we'll look at examples later. Okay, so here's an example of a convex function. You take a point x and you take a point y, any 2 points. This is a function f. This is f of x and this is f of y. Okay, so on the right hand side, I'm doing a linear interpolation between the points x comma f of x and y comma f of y. So what is this going to keep this going to measure as I vary lambda? It's going to give me the linear segment between these 2 points. Okay, this is, so as I change lambda, I'm going to be, the right hand side value is going to be basically given by the height of this part. What is f of lambda x plus 1 minus lambda y? It's basically any point along this. So if you take this point lambda x plus 1 minus lambda y, as you vary lambda between 0 and 1, it says that the function value exceeds the value, I'm sorry, is less than equal to the value along this line segment. This has to be true for every x and y and for every lambda. Okay, so the function has to have shapes which look like a cup, basically. At least in 3D, it looks like a cup. Okay, in 2D, it looks like this U-shaped thing, basically. Okay. Okay, is the definition clear? And so here's an example of a non-convex function. So that's a non, so this is convex function. This is a convex function. That's a non-convex function. So any function which, of course, it doesn't satisfy this property, it's called a non-convex function. Okay. And why is this the case? So for example, I can take points here in this example. So this function looks convex in this part, but if you take, for example, the x here and the y here, clearly the function doesn't look, if you draw the linear interpolant here, it is clearly not residing above the function value. Okay. Okay. Now what's a concave function? So a function f is concave simply if f is concave, if and only if minus f is convex. Okay. So if minus f is convex, it means simply that if you take this inequality on the top, it has to be reversed, because, so basically this is the same thing as saying f of lambda x plus 1 minus lambda y exceeds lambda f of x plus 1 minus lambda f of y. Again, for every lambda between 0 and 1 and for every x and y in Rn. Okay. So concave functions will look like this, basically. Okay, that's a concave function. Okay. Now, one of the nice things which was maybe realized about 50, 60 years back was the fact that convexity buys you a lot. Okay, and we will discuss this later. Okay. But is it clear what the two definitions are? These are the fundamental definitions of convexity and convex sets. Okay. You can, this is the fundamental definition. There are other definitions if the functions are differentiable. Okay. So, for example, here's a convex function which is not differentiable. Okay. So I see a chat. I'll just have a look at it in a bit. So here's the function which is convex but not differentiable. Okay. So there are definitions of convexity that if the function is differentiable, there are definitions based on gradients, and then there are definitions based on Hessians, the second derivatives. We won't pursue that in this part. It's not critical for us. Okay. But you can have clearly convexity is so you can have convex functions which are not differentiable. Okay. Okay. I see a chat here, so let me just see what them is. Can we download the notes for this lecture? The notes for this lecture are already there in topic one. It's the same set of lecture notes which are already there on my website. Okay. 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 Any questions with this? Any clarifications or any comments? Or okay. So what's a convex program? Okay. So we saw a linear program. So what's a convex program? Okay. So maybe I'll go to next page. So a convex program is a problem of a particular type. Okay. Minimize f of x subject to x and x in Rn. So this is very similar to what we saw as a general optimization problem, where there are a few things which are satisfied. Okay, so what I've written here is, so firstly, in this definition, I'm writing it in a minimization form. Okay, this is going to matter. Okay, the second is f, the set x, which is a subset of Rn, is a convex set. Okay, and third, so when I say it's a convex program, what are my requirements basically? Okay. Third, this function f. Okay. Now the domain of f might be Rn, but it need not be. Okay. The function might just be defined on the set capital X. Okay. So let's say the domain of x. So I'm only interested in f on the domain X, not in Rn necessarily. So f going from x to Rn is a convex function. So when you're trying to minimize a convex function over a convex set, that's a convex program. Okay. And in this problem, minimization matters. Okay. If you write maximizing a convex function over a convex set, that's not a convex program. Okay. We can play the same trick of, last time I told you, if I want to write a maximization problem, I will just minimize a negative. Okay. You can do this. But if you write minimum of f of x as a maximization problem, it will become maximum of minus f of x. If f is convex, minus f is concave. Okay. It is not like a linear function. Linear functions, if you take a linear function f of x, a transpose x plus b, this is an affine function, minus f of x is also an affine function. It's in the same class. Okay. This is not true for convex functions. Okay. Okay. Fine. Any questions with this? Okay. Why is this? Okay. So firstly, a few comments here. Why is this? Okay. So firstly, maybe I should say, why is this important? Why is this relevant? Okay, so maybe some of you have taken classes before. Why is knowing something a convex program? Why is it a good thing or bad thing? I mean, why is it important? Do any of you know this from your prior work or classes or whatever? Yeah, go ahead. It's easy to get the local optimum. Okay, so we can make that more precise. Um, yes. Exactly. So okay. So what's your name? Sorry. Tusha. Trisha. So Trisha says that for a convex program, a local optimum is a global optimum. A local minimum is a global minimum. And this is a very important property. Okay. This is not true in general. Okay. So let's try to make that precise here. So I want to make this precise. I want you to see this once at least. So let's first define what's a local minimum and a global minimum. Okay. So what's a global minimum? So this is my convex program. Okay. This is a problem I'm interested in solving. Okay. So what's a global minimum? So X star is a global minimum. X star is a global minimum. So obviously X star has to be in the set. Okay. So X star in X is a global minimum, global minimizer, or I'm going to use minimum and minimizer interchangeably here. Okay. The objective function uh, is a global minimum. Okay, maybe I'll be precise. The global minimizer. What is the definition? If f of x star It's a minimization problem. So I want it to be less than or equal to f of x for every x and x. Okay, that's the definition of optimality, a global optimum. Okay. What's the definition of a local minimum? Okay. Okay. So I need to first, so to define a local minimum, I need some notion of local, something being local. Okay. So I'm going to first start by defining a ball, and then we will define. So I'm going to define, so we need to define a neighborhood, something local. Okay. So let's define, so for any, so I'm going to define a ball. Let's call this ball a function of x, and let's call this x star and epsilon. Okay. So what is this? This is a set of all points x that are within a epsilon radius of x star. Okay. So this is a ball. So you have a point, any point x star, and let's say I'm using the Euclidean ball, so the L2 ball. Okay. So I'm taking the Euclidean distance. So that's a basically it's a in 2D it's a circle. Okay. Um, Otherwise the sphere, okay, hypersphere and so on. Okay, but that's a ball, right? It's a ball. All these points within this region are within an epsilon radius of x star. Okay. So, and of course, here for where epsilon is some uh, constant, okay, some positive constant. Okay. So, what is a local minimum? So, okay. So, x star in x. So, let's now define a local minimum. X star in x is a local minimum, local minimizer. Again, we are interested in this problem. Everything is, all definitions relate to this problem. Is a local minimizer if f of x star is less than or equal to f of x. But now I'm going to look at a local region. So if there exists some epsilon greater than 0 such that f of x star is less than or equal to f of x for every x which lies in the set capital X intersected with this ball. Okay. So when I'm looking at a local region, so I might have a very big feasible region in high dimensions, but when I look at a local epsilon ball around this region, every other point, there's no other point in this region which is strictly better than x star. And because I'm doing a minimizer, I need the signs to be in this, in this, in the inequalities to go this way. Okay. Okay. So is the definition clear? It's straightforward, but it's a useful definition because the problem, I mean, why is this? So, okay. I mean, intuitively, local minimizers should be harder to find, should be easier to find than global minimizers. Why? Because locally, I have to just figure out locally what's happening. Okay, so I could use derivatives. Derivatives are local information. I can tell you locally what's happening in the function. Globally, I need to compare. Things could be very different far away from where I am locally. Okay, so local minimizers are generally much easier to find than global minimizers. Okay, now the claim is, so the theorem is, so the first theorem we'll do today is, so for convex optimization or for a convex program, so for a convex program, x star is a local minimizer if and only if x star is a global minimizer. Okay, so if I can find a point locally where things are looking good, then I should be able to find it. Then this point is good globally too. Okay, so let's just maybe see an example. I mean, before we go, so let's just maybe just check this. Maybe just by looking at a figure. So let's take this point. Okay, so just to get some intuition, just to ensure that we all are clear on what these definitions mean. Take this function and let's take this point. Okay, locally on this side, my function value is increasing, so it's better. So this point is better than these points. But if I move a little bit to the right, my objective function is decreasing. So it is not a local minimizer. Okay. This point right here is the local minimum. Because if I go to either direction, my objective uh, is not decreasing. And this is also the global minimizer. Okay, this is of course in 2D. Sorry, it's a 1D function, but you can see this. Okay. You similarly, this point is a local minimizer. Locally, it is optimum, but clearly, it is not a global minimizer because far away things are behaving very differently. Okay, so locally, you might have thought you're doing very well, but you're not guaranteed globally you're doing the best. Okay, so convex functions in any dimension, I mean, it's it could be in one dimension, it could be in high dimensions. This property always holds. Local minimizer is a global minimizer. Okay, so that's why we can look at we can look at things like derivatives and second derivative conditions, which are local conditions, to check optimality for convex functions. Okay, okay, okay. So let's prove this result. Okay, let's. So along the way in this class, I want to do some proofs. Okay, the reason is it just helps build your concepts, helps you understand things better, and as a PhD student, I believe it's important basically. Okay, okay. So let's do. So we'll do some proofs along the way. Okay. So if a point is a global minimum, that it is a local minimum is an obvious thing. Okay, so this side of the implication. So when I say something like this, it means x star is a global minimizer implies x star is a local minimizer. This is obvious, right? It is globally the best. So if I for every x, so if I intersect it with a ball, it can only be a smaller feasible. It can only be a smaller point. So it has to every global minimum has to be a local minimum. So what you need to prove is the other direction. Okay. Okay. So we will. So let me just maybe just create a figure here, and so we will do this by. So what we want to show is if xi is a local minimizer, you want to prove that it implies xi is a global minimizer. Okay. So the way we are going to do this is we're going to assume that. So we're going to do this by contradiction basically. Okay. So let's assume that suppose x star is a local minimizer. Okay. But it is not a global minimizer. So I'm going to do proof by contradiction. Okay. So I've got a local minimum, but it is not a global minimum. Okay. So that means there is some other point which is giving me a better objective function value. Okay. What does this mean? That this implies there exists some point, let's call this x bar in the set capital X, the convex set X. Okay. Remember the set is convex. Okay. This is a convex set. There exists a point in this convex set x bar such that f of x bar is lesser than f of x star. Okay, it's a local minimum, but it's not a global minimum. Okay, so I can find a point which is obviously better in objective function value. Okay, so now what we are going to do is we are going to try to parameterize points going from x star to x bar. Okay, so let's take this point. Let's call this point. Uh, so let's say this is x star. Okay, let's say this is a point, and let's say this is a point x bar. Let's say x star was a local minimum. Okay, so I'm just drawing an arbitrary function here, a convex function. But let's say so. Let's for some reason. So let's say this was a local minimum, but it's not a global minimum. Okay. Okay. So what we are doing is we are parameterizing. We are moving from this point to this point. Okay, from x bar to x star. Okay. So we are now going to consider this point. So consider lambda times x bar plus 1 minus lambda times x star for lambda ranging in the interval 0 and 1. Okay. Let me finish the proof, and if there are any questions, I can take it after that. Okay. Okay. So as we change lambda between 0 and 1, again, we are moving between x bar and x star. Okay. As we parameterize. Okay. So let's think about, so we are now going to use convexity. Okay. So what do we know? So from convexity, f of lambda x bar plus 1 minus lambda x star. Remember, both of these are points in the convex set. Okay. X star lies in the set capital X, which is a convex set. Okay. Um, Likewise, x bar. So both of these are points. So from convexity, I know this has to be less than equal to lambda times f of x bar plus 1 minus lambda f of x star. Okay. So this is because f is convex. Okay. And now if we consider, so for lambda between, so if I now consider, so for lambda strictly in the interval 0, 1. Okay. So let's now make it a strict. So this is true for every lambda, okay, between 0 and 1. When I consider this, now if I consider values of lambda which are strictly between 0 and 1, okay, so these are strictly non-zero values. Okay, what do I know? I know f of x bar is less than f of x star. This value is lesser than this value. So I can plug in, I can write this as lambda times f of x star plus 1 minus lambda f of x star. This is true for all lambda between 0 and 1, strictly between 0 and 1, because these are now non-zero values and positive values, obviously. And f of x star, x bar is less than f of x star. Okay, so I'm using this inequality. That's my, this is because I assumed it's not a global minimum. Okay, but what is this on my right hand side? This is exactly f of x star. Okay, which is my um uh, uh I'm sorry, this should, yeah, f, this is I'm okay. You guys did not stop me. I got my inequalities wrong. You didn't tell me I got my inequalities wrong. F of x bar is my, no, this is a local minimum. That's fine. That's fine. That's fine. F of x bar. No, that's fine. That's fine. Yeah, this is fine. No, I got my inequalities right. Yeah. Okay. So what does this mean? As I now change, okay, so this value is lesser than f of x star. As lambda, so what's happening with lambda? As I'm changing lambda, I'm moving this point close to x star in this region. When lambda gets closer, so in this parameterization, when lambda is getting closer and closer to, I guess I've written this as, yeah, as lambda gets closer and closer to 0, I'm getting closer and closer to x star, right? As lambda gets closer to 0 from above, what is happening? I'm getting closer and closer to x star. But we get lambda x bar plus 1 minus lambda x star within the ball and with a strictly smaller objective function value. There's a strict inequality here. This violates the condition that is a local minimizer. My assumption, which contradicts the assumption that XR was a local minimum. Okay, so what we did is we basically parameterized. We moved in a linear, so I moved the points here. Because of convexity, the function looks something like this. Within a ball, I can, from the convexity, from the definition of convexity, I can get close to this. I can get close to this point within some ball and have an objective function which is strictly smaller, contradicting my assumption that it's a local minimum. Okay. 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 Any questions with this proof? Is the argument clear? Any step you want me to go through one more time, or? So one of the things I want is along the way is for you to get, I mean, if those of you like doing proofs, that's great. If you don't, it's a useful tool because, it just helps you. You will do the other parts of your courses. on other, when you do your own research, you'll be using it. Okay. Okay. So this is a simple, but it's a very useful property. Okay. That for a convex program, a local minimizer is a global minimizer. Okay. So I want to make a couple of notes here, which we will do next. But any questions with the proof? Otherwise, I'll move on. No? Okay. So let me make two notes. Okay. So I want to make two notes. The first one is just so first thing I want to claim is, so actually I should not, maybe this should not be a note, this should be a claim. Okay. So I claim that uh, LP, and this is easy to see, LP is an instance of a convex program. So what the class of problems that we are going to study in this course, at least in the first part, is just a special case of a convex program. Okay. And why is this the case? This is fairly, I mean, this is straightforward to see. What is an LP? LP is of course minimized. I can write, I can focus on this form. We know that every LP can be written in this form. Let's take this form. I need my objective to be convex. A linear function is the simplest form of a convex function. Okay, what is the definition of convexity? You take 2 points x and y. Okay, you check that for you compute C transpose, you take the objective function C transpose lambda x plus 1 minus lambda y. This is exactly C transpose lambda x plus C transpose 1 minus lambda y, which is exactly lambda times C transpose x. Lambda is a scalar, plus 1 minus lambda times C transpose y. That's the objective function at this point. It's a linear combination of, in fact, it's a convex combination of the objective functions at x and y. We required in the definition only this to be less than equal to. So actually, this linear functions are both convex and concave. Actually, it's both. It satisfies less than equal to and greater than equal to. So this is clearly a so a linear function is a convex function. Okay. So this satisfies the definition. In terms of the feasibility, if I give you 2 points, ax which is greater than equal to b and ay greater than equal to b, and now you take a point lambda x plus 1 minus lambda y. Again, I do a times, so I apply so I do a matrix vector product. This is exactly a times lambda x plus a times 1 minus lambda y, and this is lambda times ax plus 1 minus lambda times ay. And here, of course, in this part, in this equality, I really didn't require any assumption on lambda to be non-negative, I mean, between 0 and 1. Here I require it because this is going to be greater than equal to lambda times b plus 1 minus lambda y, b, when lambda is between 0 and 1. Okay. Okay, here I require this. Okay, because ax as a vector exceeds b, is greater than equal to b, and lambda is a non-negative number. So when I'm adding a non-negative, when I'm multiplying a non-negative number on both sides, the inequality stays. Similarly, 1 minus lambda is a non-negative number. So this inequality is true only when lambda lies between 0 and 1. Okay, but that exactly defines, and this is exactly equal to b. This defines a convex set because this point now also lies also lies lies in the feasible region for all, because of this inequality. So a times this point is greater than equal to b, so that's a convex set. Okay, so LP is an instance. In fact, it's probably the simplest instance of a convex program. Okay, so for a linear program, if I find a point which is locally optimum, it's basically telling me I'm finding a point which is globally optimum. Okay. Okay. Any questions with this? Okay, I want to make a second note here. This is something which is a bit, I mean, I want to be a bit, I mean, okay. Okay, so I just want to make this point because it's a source of confusion sometimes. I find this sometimes with, because people learn about these topics in different forms. So, firstly, I should say convexity is a very attractive property. Okay, convexity is a is an attractive property for optimization because local guarantees can be translated to global guarantees. Okay, locally, if I can, for example, if I can compute derivatives and I can check locally that it's a local minimum, then I can you can use second derivative conditions. You're guaranteed global optimality. So it's very good property. You don't have to search everywhere. However, if you want to say that a convex program is solvable in polynomial time, it's efficiently solvable, you need some additional conditions. Okay. So as soon as you say something is a convex optimization problem, it doesn't become efficiently solvable. Okay. And I found this a source of, I mean, sometimes I find this so as soon as you say something is a convex optimization problem, it doesn't become easy to solve. Okay. In high dimensions. Okay. You require something else. You require to be able to compute either the gradients or subgradients efficiently. When we look at the feasible region, we need some properties of the feasible region. Okay, so I want this to be, and again, we'll come back to this when we talk later about the ellipsoid method and so on. We need some additional properties. It's a very useful and very beautiful property, and it's generally when problems are solvable efficiently, convexity becomes an important property. But we need some additional conditions for efficient, or what we are going to later on discuss, polynomial time computability of the convex program. I mean, to solve it in polynomial time. Okay. So again, there's a little bit going forward at this point. But I just want to make this point immediately. So don't think if you have a convex program, immediately it's easy to solve. Okay. This is not the case always. Okay. It depends on how the convex program is given to you. Okay. How is the input specified? And what can you do? We will talk about later on things like computing the subgradients, doing a separation oracle for this, and so on. At this point, I don't want to get into this. I just want to say that you need some additional conditions. Okay, so this is just a caveat. Just keep this at the back of your mind. Okay. Okay. Any questions? Online audience, any questions? Okay. I will spend. We'll discuss one more property maybe, and then, or shall we take the break now? Uh, Maybe let's take an early break today. It's okay. So let's take a break now. It's 10:50. If you've got questions, you can ask me, or we'll start in about 5 to 7 minutes. We'll start the class. Okay, so we can take a break. Okay, if you've got questions, you can ask. Yeah. Any questions from the online folks? Your bachelor's was in maths. Yeah. Your bachelor's was in maths. Your bachelor's statistics. Your bachelor's it's called GM. Your bachelor's. Okay. So what you have is math better. Okay. So you love doing proofs. That's good. So may I'll just respond to your question here. So there's a question about do we consider differentiability for convex functions? Yes, it's going to be. I mean, if you have convex functions which are differentiable, it's going to be very useful for you because you can just find the points where the first derivatives are equal to zero, and that will tell you your global optimum. Okay, so that's a useful property if it's differentiability. You can use gradient-based methods to solve it. But basically, wherever the derivative is zero, you will get global optimality. The tools that we will use for linear programming and for integer programming will be not be gradient based. The algorithms here will not be gradient based for this course because there'll be a bit more combinatorics which will show up here, as you will see. Yeah. Okay. Let's maybe get started again. Uh, okay. Okay. So we discussed what's a convex program. We discussed the fact that for a convex optimization problem, a local minimum is a global minimum, and LPs are an example of a convex program. Okay. Now, one thing that we can do is we can go beyond just what looks like a linear program. So there are slightly more generalized classes of optimization problems which are very useful, which may not be a linear function at first at a first glance, but by some analysis, we can transform it to a linear program using this convexity lens. Okay, so I want to start with the theorem, and then we will see how to apply it. So there are many. Okay, so we define what a convex function is. Convexity is, so when I sum up two convex functions. So for example, if I take a convex function f1 and f2, both of which are convex, okay, then a function like alpha 1 times f1 plus alpha 2 times f2, where alpha 1 is a non-negative number and alpha 2 is a non-negative number, is also a convex function. Okay, so there are many properties, or there are many mathematical operations which preserve convexity. And so if you do a class in convex optimization, they will, or convex analysis, they will talk about this, what type of properties preserve convexity. Okay, for us, the property that I'm going to be interested in for this course is the following result, which is a useful one because it's going to help us solve some other LPs. Suppose I give you m convex functions. Okay, so suppose fi going from Rn to R, so I've got m convex functions. Okay, a very useful function which is going to be convex is, if you define f of x as the max over all these m functions evaluated at the point x. Okay, so you take a point x, you check the function value at each of these points x, fi of x, and take the maximum of them, then f of x, where again f of course goes from Rn to R, is also convex. Okay, so this is a very useful property of convex functions. You take convex functions and you take the max of convex functions, it's also going to be a convex function. Okay, so this is a very, very useful property. We can first check, we can just visualize this first, and then we will try to do a proof. So again, I'm doing everything here in 1D, but all these things go forward in higher dimensions. Take one convex function, take another convex function. Okay, so this is f1. Let's say this is f2. Okay, maybe a third convex function, f3. If I ask you what for term by term the maximum. So if I ask you what is, sorry, my drawing is not very good. Okay, let me just be careful. I'm drawing this, it looks convex. Okay, so if I think about what is this f of x in this case, f of x would look like this, right? You take the maximum value. Okay, so this quadratic part or whatever, this part is there. In this part, there are three functions, but the maximum is attained by this part. Then in this part, maximum is attained by here. There are three parts, but this one is attains the maximum. And here, this part is attaining the maximum. So this is how f of x will look. This is the function value. Different functions take the maximum value at different points. This function, f, is also convex. If you see the shape, okay, it also has this convex, it will satisfy the convex function. It has a shape. Okay. Okay, so you can see this in a figure. Okay, it's straightforward to prove this, but I want to prove it. Okay, because a very useful property for convex functions, maximum of convex functions is also convex. Okay, so let's prove this. Is the statement clear? What is the function I'm looking at? Is it clear? Okay, so let's prove this. Sorry, proof. Okay, so again, I'm going to consider 2 points, x and y, and we're going to just work with the fundamental definitions of convexity. xy in Rn and lambda in 0, 1. And we're going to check what happens to f of lambda x plus 1 minus lambda y. I want to ensure that this function satisfies the convexity property. So I'm going to start by first using just the definition of the function. So from definition, I'm just taking the maximum of all these convex functions at this point, lambda x plus 1 minus lambda y. Okay. Now, we know that each Fi is convex. So each Fi satisfies the convexity definition. If each Fi is lesser than equal to lambda times Fi plus 1 minus lambda times Fi, the maximum also has to be less than the maximum of these. Okay. Since each Fi is convex, right? So what I'm using here is simply the fact that this function value is lesser than equal to this function value for every I. And by taking the max of these numbers and the max of these numbers, it also has to satisfy the same condition. Okay. Okay. Now I'm going to use uh, the subadditivity of these max functions. So this is the same. This is also less than equal to max of I from 1 up to m lambda fi of x plus. So I want this max operator. I want to distribute it across the two functions. Max of I from 1 up to m 1 minus lambda fi of y. Why is this the case? This is because since if you think about taking the max, let's say, of a set of numbers, ai plus bi, if I find the best ai and the best bi, it has to be an upper bound. Okay. This property is called subadditivity. Okay. This is basically the subadditivity of the max function. Subadditivity. Subadditivity of the max function. Basically, picking the individual best of each of them and picking the maximum of each individual one has to be better, at least as good as picking the max of the sum, basically. Because I've got more choices in the latter case as compared to the former case. And now because lambda is non-negative and between 0 and 1, this is a non-negative number and this is also a non-negative number. I'm taking the max, so I can take this non-negative number outside. So this is simply lambda times max of I from 1 up to m fi of x plus 1 minus lambda times max of I from 1 up to m fi of y, and well, this is exactly f of x and f of y. So I'm done. We approved. Okay, so I'm going to put a hash here whenever I approved. This is exactly f of x and this is f of y. So I'm proving that f of lambda x plus 1 minus lambda y is upper bounded by lambda times f of x plus 1 minus lambda times f of y. Okay. So we use basically the fact that each fi is convex and the fact that this max function is a subadditive function. Okay. Okay, this is a very useful property. So if you have convex functions and you take the max of convex functions, it's also a convex function. Okay. Okay. Any questions with this? So why is this useful? So let's take. So we spoke about LPs. So I'm going to look at a slightly more general class now of problems. So I'm going to call this piecewise linear convex optimization. Okay. So we did linear optimization, or at least we discussed linear programs or linear optimization, convex optimization. I'm now looking at a class of problems. I'm going to define this problem. So what is this problem? I want to minimize subject to, so there are constraints, let's say linear constraints, max I going from 1 up to m ci transpose x plus di. Okay. So my input for this problem, what is my input to my piecewise linear convex program? Basically now there is these vectors c1 up to c. So these are vectors now. Okay. Cm, all of these are in Rn. that is D1 up to DM. All of these are in R. Okay. Each of them is in R. Uh, okay. Uh, all these are given to me. Okay. And then you have the standard A and the B. Okay. So what is changing? The fact that I now have many terms in my objective function and many constants, maybe D's potentially. But now I'm taking this function and I'm interested in solving this optimization problem. Okay. This piecewise linear convex program. Okay. First thing is, why is this a piecewise linear convex program? We just saw that the max of convex functions is convex. This is a linear function. That's a convex function. So this is clearly piecewise convex, but not only that, is piecewise linear. Okay. So this is a piecewise linear convex function. Okay. So remember, piecewise linear convex functions, for example, in 1D, these functions might look something like this. Okay. The function would look, so if you were to look at this as a so there are, this is C1 D1, C2 D2, C3 D3, C4 D4. If you were to try to look at what this objective function here is giving you, it's essentially giving you the max. So it's this part. Okay. So this is also actually a convex optimization problem. However, this is not a linear optimization problem at this point, because the objective function is not a linear function. This function is not a linear function. It's a piecewise linear function, but it has particular shape. It is convex. Okay. Of course, you can have piecewise linear functions which are non-convex. Okay. If you take a function of this type, that's a piecewise linear function too. It's non-convex. Okay. Okay. These type of objective functions will have functions which look like this, not like this. Okay. So this is piecewise linear, but clearly not convex. Okay. We already know from convex optimization that this is also a convex program now, because this is also a convex function. So this is a convex program. Okay. What we can do is we can actually convert it to a linear program. It's not a linear program, but we can convert it to a linear program using this idea of what is called the epigraphical reformulation. Okay, so the idea is actually very simple, but it's a very useful idea which will show up again very often in many cases. Okay, so let's ask ourselves the question, what is the objective? It is this part, right? Maximum. How can I write this? The max. So for any given x, okay, so think of x as being fixed now. I'm just evaluating this function. It's a function evaluation. So I give you a particular x. I want to evaluate the function. So it could have been this point, this point, this point, or this function all the way down. There are four values. I want to pick the maximum. I can write this as minimizing t subject to t exceeding the max. Okay. So the decision variable in this problem is a single variable t. Okay, this is my decision variable now. And I'm basically finding the max very simply by saying t has to be bigger than the maximum value. So if you think of what t is, so now if you think of t along this axis, along the y-axis, for a given x, t has to exceed or has to be greater than equal to the maximum function value. There's either this value, this value, this value, or if I take the function all the way down, there's a point somewhere way down here. Okay, it's really not going to be the maximum at this point. Okay, t has to be exceed this number or be greater than equal to this number. I want to minimize t, which means I'm going to push this value all the way down to this value. Okay. Now this is actually okay, fine. So now what do we do? This is still not a linear program, but now we can use the simple fact that if I want t to be greater than the maximum, t has to be greater than each of them. So I can write this as minimizing t subject to t exceeding ci transpose x plus di for every I from 1 up to m. Okay. If I want t to be greater than or equal to the largest of a set of numbers, t has to be greater than or equal to each of the numbers. Okay. So I'm disaggregating the constraints. Okay. Now we can do this at any point along this figure. Okay. So if you take any x, right? If you take this point of x, t has to exceed for this particular value of x, there's a fx, 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 and a fx. T has to exceed each of them, and I want to minimize t. So the objective function is important. So it will move it down to this level. So what we are creating is we are looking at this basically this part of the feasible region. Okay. And we are trying to, for any x, we're trying to minimize the t. Okay. And that gives, so if I solve this problem, I will find the best t for the given x. Now the problem is I don't know what is my best x. Okay. For this problem, my minimizer is clearly this point. Okay. Global minimizer. So I need to still search for x. How do we do it? Very simple. We, sorry, we, sorry, I'm just trying to figure out how to close this. Okay. So what do? We simply have to, so I want to solve the LP, right? So I want to minimize, yeah, uh, uh, maximum Ci transpose x plus di subject to ax greater than or equal to b. But now I can rewrite this as to minimize. So now think about what I'm doing. I'm taking this part and writing it as another minimization problem, this form. I want to minimize over x and minimize over t. I can do a joint minimization. I'm working together. Okay. So I'm going to minimize t subject to t greater than equal to ci transpose x plus di for I going from 1 up to m and ax greater than equal to b. Okay. This is a formulation which involves, if originally there were x's in Rn, there are Rn variables, and there's a variable t which is R. Okay. So if I had n variables, I have n plus 1 variables now. I'm optimizing over both x and t. If I had originally, let's say, k constraints, now I have k plus m constraints. Okay. But this is a linear program. It's linear in t, it's linear in x. So we took a piecewise linear convex program and wrote it as a LP. Okay. This is a very useful trick which will show up very often. Okay. So it should be something you're comfortable with. Okay. We can use this in different ways. Okay. Okay. There's a term for this which I also want to just mention. It's called the it's called the so this also I just wanted to know this term. Note. So this is known as the epigraph. This is referred to often in the literature as this is referred to as the epigraph reformulation. So what's the epigraph? Okay. So if I give you a function f, so if I given a function f going from Rn to R, okay, the epigraph of f, f, okay, it's in Rn. Okay, so I'm going to move it up one variable. So I'm going to go t and x. Okay, that t exceeds f of x or greater than equal to f of x. Okay, so you look at all the values of x, and for every value of x, you find the t values which are exceeding greater than equal to f of x. So in this case, like this is the epigraph reformulation. I'm looking at all the x's and all the t's which are greater than equal to f of x. Okay, so it's a set given by this. It's an Rn plus 1. Okay, this one. It's called the epigraph reformulation. So this will get used a lot. And one of the important things about convexity, and I will not, you can see this here, but so I this you can do at your own. Okay, so try on your own this claim. F is a convex function if and only if the epigraph of F is a convex set. Okay, you can try this on your own. This is not key to our class, so you can try this. It's again a simple proof. Okay, just from first principles you can do it from the definition. But basically, if you think about what the set looks like, right? What is the epigraph here? The epigraph here is essentially all this part. All this is the epigraph, right? The entire thing is a convex set. If you look at the set, it's a convex set. Okay. So the claim is for any convex function, the epigraph will always be a convex set. Sorry, it's an if and only if condition. Okay. Okay. Any questions with this? It's a very useful reformulation, the epigraph. Okay, it'll come up. It's a useful trick to know because what happens is, and I'll show you an example next of why this is relevant. I'll do an example of how you can use this. Okay, because there are many problems which you can formulate as piecewise linear convex functions. Okay, and another thing is another technique. You may not want to use this always, but if you have a convex function, if you have a nonlinear function, you can approximate it with linear functions. Okay, so there are techniques of this type too out there. Okay, but let's take a problem. So let's take an application. So I want to do an example next to illustrate how you can use this. And I thought we'll do an example, maybe slightly more. We'll do a form of regression, but we won't do L2 regression like standard least squares regression. That's a quadratic program. I'll do a variant of it. There are many forms of regression. So, some of you are statisticians here, so it should be of interest to you. So let's take the least absolute deviation regression. It's a type of regression. I'll formulate it. Okay. And I'm going to put here with something called a lasso penalty. I'll explain this. Okay. Okay. So I want to first recollect. Okay. So recollect. So I want you to first remember what the norms of vectors are. Okay, we're going to just use a few norms here. So what's the norm that you might be most familiar with, or I mean, you should be familiar with is the L2 norm for sure. Okay, it's x1 squared up to xn squared. There's a generalization this for any p. Okay, but we'll focus on two more norms here. The L1 norm. So this is the L2 norm. Okay, so what's the L1 norm? Is the sum of the absolute values of the values xi's, and the L infinity norm is the max, not the sum, but the max of the absolute values. Okay, so these norms satisfy several properties like triangle inequality and homogeneity and so on. I don't want to get into all that here. It's not critical for us. Okay, but we are going to use these norms because these norms give you a measure of distance. It is the most common form of distance. Okay, so we're going to use this. So I'm going to use this for setting up a regression type problem, and we'll talk about how you can formulate it as an LP. Okay, so let's do an example. So suppose I give you a regression problem. So given pairs x, so now xi and yi are not going to be decision variables. Okay, so what are xi and yi? This is basically xi is a vector now, let's say in Rn. Okay, And R for I going from 1 up to M, I want to find the best fit. Of course, we have to define what a best fit is. Linear model to describe Y using X. Okay. So this is a standard statistical regression problem. I'm given pairs. This is a vector. X could be in very high dimensions. Okay, it could be anything you're using to predict an output of interest. Okay. Okay, and I've got M such points. Sometimes in statistics they will use N for the number of points and D for the dimension. I'm going to use the optimization. So if for those of you who do statistics, these N is typically used for number of points and D is used for dimension. Okay. So don't get confused. You can use whatever as long as you understand what you're doing. Okay. So here N is the number of, so here M is the number of points and N is the dimension of my problem. Okay. So what is the least squares problem? We know, but I'm going to take the least absolute deviation regression problem. It basically says I want to minimize the L1 norm. Okay. So the L1 norm of the output of interest, which I'm trying to predict using a linear model. So I'm going to take a linear predictor subject to alpha being in Rn and beta being in R. So beta is my intercept or my constant term, and alpha is the importance given to each component of the X vector. Okay, so that's a L1. So this is a least absolute deviation, least absolute deviation fit. Okay. So you would have no in your first class in statistics, you would have solved this with a quadratic functional form. Okay, you would have had a L2 form. There are L1 forms of this problem, and there are reasons why you might use one over the other. So we're going to look at this class of problems at this point. Okay. Okay. Now this is the absolute function is a piecewise linear convex function. Okay. So what is the absolute function? So if I take z, the absolute value of z is this function. It's a piecewise linear convex function. Okay. So I can rewrite this problem as a linear program. Okay. Now that is uh, one thing you need to you need to think about, which is there are a couple of ways you can write this linear program. Okay. Because this is not a linear program clearly. Okay. But it's a piecewise linear convex function. Okay. So we can reformulate this as an LP. Okay. And there is a sensible way of doing it, and I would claim a less sensible way of doing it. Okay, or rather a slightly crazy way of doing it. Okay, so we can reformulate it as an LP. How? We will use the epigraph reformulation, except we will do it term by term. Okay, so what I mean by this is I will rewrite this as minimum summation I going from 1 up to M. Previously, I had a single variable t. I will have one for each term, subject to ti exceeding the absolute value of these two numbers. Okay. So this is clearly not a LP at this point, but let me just write it anyway. This is an equivalent formulation. Okay. So whenever I say something is an equivalent formulation, it means I can solve, if I solve this problem, I solve that original problem. Okay. Again, alpha is in Rn and beta is in R. This is not a LP at this point because this is still a nonlinear function, but I can reformulate this using the fact that the absolute value of a function, absolute value of z, is the max of z and minus z. Okay. So this is simply yi minus alpha transpose x minus beta I. for every I, and Ti is greater than minus Yi. So I took the this number could be positive or negative. After I do my fit, I account for both. Okay. And then I've got alpha and beta. There are no constraints on them, so I don't really have to write them down, but I'll just put it down for completeness here. Okay. So this is an LP. This is not an LP because of this part, but this is a LP. Okay. So we can write this problem as an LP. So if I have an algorithm for an LP, I can solve this problem basically. Okay. Now there is a slightly less sensible way of writing this problem out. Okay, which is if you think about this absolute value, sums of absolute values, you take every possible combination of it being positive or negative. Okay, so you take. So what I mean by that is, if I give you something like this, max of x1 minus x1 plus max of x2 minus x2. If I give you some, if these are numbers, okay? What I did in this problem was I created one variable for this, T1, a T2 for this, a Tn for this, okay? You can, of course, rewrite this as a big max function of many linear functions, okay? So you can write this as max of x1 plus x2 plus xn, okay? Minus x1 plus x2 up to xn. I can write this minus x1 minus x2 up to xn. I can create many of these linear functions. In fact, I'll have to create how many? There are two possibilities for each one. How many linear pieces will come up here? Two possibilities here, plus or minus. Two possibilities here, plus or minus. I do every combination. So it'll be 2 to the power n linear terms if I do this approach. So I can write this function as a max of 2 to the power n linear pieces. And then I can use a single t variable and solve it. But this is a crazy way of solving the problem. You started with a problem which was nicely behaved. You suddenly went to something which is exponential in n just because you wanted to use this trick. But there are other ways you can use this trick. Okay. So you have to be careful when you do some of these tricks. So I don't want to. So what I'm doing is we are just creating a single epigraphical variable for each individual observation or pair. Okay. Not a single one for the entire sum. Okay. So you'll have to be careful with some of these things when you do your formulations. Okay. So this is not a good way to model the problem or to solve it. Okay. To formulate the problem. Is that clear or is it a bit too abstract? I don't know. Is that clear to all of you or it's not clear? Is it obvious? Then I can move on. Or am I confusing you? It's okay. So what you would do is, if I was to use that approach, maybe I'll just show you. Just some of you are looking a bit confused. So I just want to ensure I'm not confusing you. Another way I could have solved the LP, I could have written the LP was like this: minimum t subject to t greater than I need to think of the best way, but summation I going from 1 up to m yi minus, okay. Except here now, I will put there will be a combination of plus and minus ones. Okay, sometimes I'll put plus one, sometimes I'll put minus ones. I'll do this 2 to the power n times basically with all combinations. This is also an LP, but it's an LP with exponentially many constraints, which is a bad way to solve the problem. You don't want to go to such a transformation. Okay, so you want to be sensible about it and keep it sensible. Okay. This is also an LP, but it's just a very bad way of solving this problem. Okay. 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 Now there's another approach you can also use it, which is the same. So I want to show you one more trick just to ensure that we all are clear with this. If you take this function, another approach you can form, so another LP formulation for the same problem. I've already given you two, one of which was a good formulation, one which was not a good formulation. The third formulation, which is equally reasonable, is this is not an epigraphical reformulation, it's a slight variant. You create two variables for every observation. Okay. Again, remember X is not a variable in this problem. Okay. Alpha and beta are variables. So this is alpha and beta are variables, X and Y are given. So don't, so if you think these are nonlinear functions, they're not. They're linear functions in alpha and beta. Okay. Ti, so for every I, Ti plus and Ti minus are non-negative for every I. Okay, so this is a different LP formulation for the same problem. Okay, so previously I did it by doing this epigraphical reformulation using the greater than equal to signs and writing the max of two parts as individual pieces. Now I'm writing two variables for every observation. I'm writing the sum of those two variables. These variables are non-negative, and I'm writing in the constraints, I'm writing the contribution to my objective, the value, the fit value as the difference of these two numbers. Okay, what is this doing? Okay, I claim this is a valid LP formulation. Okay, firstly, these two numbers are non-negative. Okay, so this number, when you're solving the problem, it could be a positive number or a negative number. We don't know. Okay, but you can write any number as a difference of two non-negative numbers. This we know, positive or negative. I can write any number as a difference of two non-negative numbers. So for example, if this number took a value, let's say 3, okay, I could have written this as a difference of 5 minus 2. So if this number was 3, this could have been a 5 and this could have been a 2. But this cannot be optimal because my objective function is minimizing the sum of these two numbers, 5 plus 2. It is clearly better for me to write this as 3 minus 0. It reduces the objective down from 7. The contribution to the objective here would have been 7. This is Ti plus and Ti minus as compared to 3. This cannot be a minimizer. I have to move it down to this when I solve the optimal solution. When I find the optimal solution, this is a much better, this is an optimal Ti plus and Ti minus compared to this. Similarly, if it was minus 3, okay, I could have written this as 2 minus 5. It would have also contributed 7 to my objective, but this cannot be optimal. It is optimal for me to write this as 0 minus 3. This will contribute 3 to my objective. This is optimal. This is not, this is also optimal. So this cannot be optimal. So what is going to happen in this problem is at optimality, so you can claim that at optimality, at least one at least one of Ti plus or Ti minus must be 0. I mean, of course, both can be 0 if I get a perfect fit. Okay. But at least one of them has to be 0. If not, I will, if both are strictly positive, I will decrease the values, keeping the difference the same and decreasing my objective function. So it cannot be optimal. Okay. So this is a valid fit. So what this will do is, if this number was positive, it will give the positive value to Ti plus. That's why you put the positive value here. If this value was negative, it would give the magnitude of the number to Ti minus. Okay. So this is also a very standard trick which gets used in LPs. Okay. Any questions with this formulation? Okay. Now, there are other variants of this problem. Okay, so you can also reformulate. So I want to show you another variant of this problem, because in the past maybe 20 years, people have, of course, been interested in fitting the data very well using different. This could be, of course, we are doing LPs here, which is why I looked at the L1 norm. L infinity also works. If you have a L2 norm, that will be a quadratic program. Okay, but let's focus on LP for now. So this is L1. So this is fitting the data with alpha and beta. But in the last 20 years, there's been an interest in trying to make the model simple. That is to keep the model complexity small. How do you do this? You basically do something called apply a lasso penalty. So it's basically you take the L1 norm of alpha. This is called a lasso penalty, which is basically uh, uh, for it's for regularization or for model complexity. Okay, so what is this trying to do? This lambda here is a fixed number. It's a regularization parameter. It has to be fixed. Okay. If lambda is fixed, it is trying to penalize if the alpha values, the magnitude of the alpha coefficients are very high. So if many of the alphas go to zero, this value will go down. Okay. So the idea is you're trying to make, if these are very high dimensional vectors, xi's, and you want to only use a few predictors potentially to solve it, to fit the data, you try to use this penalty. Think about what this penalty is. It's also a piecewise linear convex function. So again, this entire problem here can be solved as a LP, can be solved as a LP for a fixed regularization parameter. Now, what happens in practice is you don't know what these lambdas are. You're trying to trade off between fitting the data and keeping the model. You want to get either good, you want the alpha vectors to have low norm, or you're also hoping for good out of sample properties. So what they typically do is they try to find lambda using cross validation. Okay, so you have to play about. So you do cross validation, and you have to solve a sequence of LPs. Okay, for every lambda, you have to solve a different linear program, and then you try to find the best lambda by doing some cross-validation idea. Okay, you keep some hold out sample, and then you check how it performs and so on. I mean, this is in the scope of statistics. It's not in interest in this course. Okay, but those of you who are interested in statistics will be interested in this. Okay, okay. The point here is this is also a linear program. Okay, okay. Any questions with this? Okay, so I want to. Any questions online? So I want to just, so we have about 10 minutes left. I just want to end with a couple of points. So I want to just introduce one more inequality, which is just useful to you, for you to know for convex functions. And then I just want to show you some code just to illustrate, I mean, we won't go through it here, but at your own time, you should implement some LPs too. Okay. I won't do it in class, but it's best done at your own time. Some of the practice questions might require you to solve LPs. Okay, either analytically, of course, that's only for practice to ensure you understand the steps. But typically, of course, you'll do it using the computer. Okay, so I just want to show you that too. But I want to start. I want to end with one additional inequality for convex functions, which is useful to know. So I just want to because this is a property of convex functions, which will show up also very often. Okay. So I just want to introduce this here, just to ensure that we cover this. Okay. So imagine I give you a so suppose I give you a differentiable convex function. Okay, a differentiable convex function. Okay. So I gave you a definition. An alternate way you can think of a convex function is If you take any point x and you take a point y, okay, f of y, so for convex functions, what will happen is